Welcome, welcome, welcome. Welcome back to class to 8.1. Talking about geometric mean today. So, when we talk about means, there's two different kinds of means. There's one we call arithmetic mean and one we call geometric means. Now, the geometric means is what we're learning today. So, arithmetic mean is something you've done for a long time. It's your average of two numbers by addition. For example, here the number 2 and 8. The mean of that is 5 because we take 2 plus 8, we get 10, and then we divide that by the numbers we have. In this case, we have two numbers, and we get 5. All right? Right. So we always done that version of it. So what we're going to be doing is geometric means, meaning we're going to use geometric shapes. But to do so, you got to look at how the numbers work. So a geometric mean is the average of two numbers by multiplication, meaning we're going to take the two numbers, 2 and 8, and we're going to multiply them. So 2 times 8 equals 16. Now, how do we get the mean of 4? That's the real question. We square root. That's the reason we took a whole lesson on square root. When we square root 16, we get 4. That is geometric means. You will multiply, then square root. Now, back in chapter 7, we talked about proportions, and it was in the form of a over x equals y over b, where the first one and the last one were called our extremes, and then these two were called our means. Now here, it's 4 different letters because we compare 4 different parts. So in this chapter with geometric means, we're taking 2 parts and comparing them to 1. So this time the x, our mean value, is the one that has some sort of relation back to the 2 other values, a and b. So we're going to find the geometric mean again, this time of 2 and 7. We set it up in this form. 2 over x equals x over 7. Now, the math of this is still the same. We cross multiply, so x times x is x squared. 2 times 7 is 14. Now, again, the reason why we have to square root is because of this. Because this is a squared variable, to get rid of the square, you square root it. So we square root both sides. So x squared is just x. Now 14 is not a perfect square, and the only factors of 14 is 2 and 7. So we will leave it just as radical 14. That's our answer. So same thing. Let's do that again for 4 and 16. So if you want to try yourself, you might want to pause this. If not, just follow along. So with 4 and 16, we said the same way. 4 is to 16. Not 4 is to 16. 4 is to x, because we don't know our geometry mean. 4 is to x, as x is to 16. Cross multiply, get x squared equals 64. So, from here on out, we're going to go ahead and square root both sides. We end up getting x equals 8. 8 is the geometric mean between 4 and 16. Now this theorem right here is just a theorem that you have to state to kind of, it's the basis to what's coming up. So this theorem is saying that when you draw an altitude. Now the altitude is a perpendicular line from one end to the other one. Now not necessarily perpendicular, so if we had a triangle that was sideways like this, and this is a right angle right here, it's perpendicular to the opposite side. So it goes from here straight across and makes a right angle right there. So the line isn't necessarily perpendicular straight, but it does make a right angle with a certain side. In this case, it's always going to be the hypotenuse. The hypotenuse will always be across from the right angle. So here's our right angle. We drew a line from this corner straight down to make a right angle right there. So when that happened, it split this triangle up into 2 smaller triangles. Those 2 smaller triangles are proportional to the big original one and to each other. That's why we say triangle AXZ is similar to triangle BXY, which is then similar to the original big one, CAB. They're all similar to each other. Okay, that's all it's stating. Now that we know that all 3 triangles are similar to each other, we can then use the next part right here. All right, so this is called a geometric mean altitude theorem. The altitude is very important because we're going to be using the altitude to figure out the relation of these two smaller sides of this triangle. So again, when the altitude was drawn, it split up this hypotenuse into two smaller, similar, proportional parts. These are proportional in some sense to each other. The way to compare it is that they're saying this smaller side, x, is similar or is to z, so x is to z, so side is to the altitude, as this altitude is to the other side. Altitude is to the other side, so side. Now again, geometric mean altitude theorem is stating that the altitudes in this case are the geometric means. Again, they're the ones that are going to be exactly the same. Geometric means are the ones that are the same, and then square root it. So again, side is to altitude as altitude is to side. Side to altitude, altitude to side. Now x, y, z, these are just letters I made up. They can have numbers, shapes, doesn't matter. Just know that we're taking one side over the altitude, and they're going to set that equal to the altitude over the other side of that same one side. So for example, here we have the number 2. It tells us 2 is x, it tells us 8 is y. We want to look for z. So to do so, we set a proportion again. Side is to altitude, so 2 is to z, as altitude is to side. Z is to 8. We then cross multiply because z squared equals 16. Now again, the reason we then have to square root is because of this. This variable, our unknown, is squared. To get rid of a squared value, you square root this side. But what you do to one side, you have to do to the other side. So when you square root something square, it gives you just the base value. In this case, it's z. But when you square root 16, you get 4. So that means our geometric mean and our altitude is z. I'm going to go ahead and erase this. But let's say this time, they give us our geometric mean. They tell us the value of our altitude. And they want us to find the value of a different side. We're going to use this ugly green right here. So this time they say this right here, one of the sides is 4, but the altitude is 6. We're looking now for that right there. We're looking for the other part of the side. You still set it up the same way. You still use the same proportional value. You say side is to altitude, 4 is to 6, as altitude is to side, as 6 is to y. So we cross multiply. 4 times y is just 4y. 6 times 6, 36. Now, the reason this time we do not have to square root is because there's nothing squared. It's just 4 times y. So we have to solve for y this time. To do so, we divide both sides by 4. In doing so, we get y by itself over here. And then 36 divided by 4 is 9. That's our answer right there. Now on this second theorem right here, I guess the third one, the geometric mean leg theorem, this time the legs are going to be the geometric mean. So in this case, AA and BB. Now which one do you use? What's dependent on the information they give you. But let's look at this. We're going to do it in one color. So here, we're going to do this in green, comparing this. We're saying the hypotenuse of the whole big triangle is to its small leg. So hypotenuse is to small leg as, and I'm going to do this in red. No, let's do blue. As the hypotenuse of this triangle is to its small leg. So we're comparing the big triangle's parts to the small triangle's part. To hypotenuse to leg, and then hypotenuse to leg right there. That's how we do C over A and A over X. Ooh, let's go back. On the second one, this one they're still doing comparing the big triangle to, this time, the larger of the two triangles. We're comparing hypotenuse, C, to its large leg, its personal large leg, as the hypotenuse of this triangle to its large leg. So do you see how we didn't use z in either one of these versions? You should not use the altitude when comparing the sides triangle, because the altitude is interior. That's the whole point of this other theorem right here. Deal strictly with the altitude. That's a whole another thing on its own. So you should never mix the value of z with a and b at one point, these two legs. You can with these two sides, but not those two. But looking back here again, one more time. We're doing hypotenuse to small leg, and then hypotenuse to small leg of the small triangle. Or we do hypotenuse to large leg, and then hypotenuse to large leg of the larger triangles. So let's kind of try that out. So on this first one, they tell us that the value of c is 29, and the value of x is 3, and we're looking for a. So if they gave us this x and we're looking for a, so we're going to use this small triangle as the part that we're going to compare to the large one. So again, we're going to do hypotenuse to small leg, 29 is to a, as the hypotenuse on this small triangle, a, is to its small leg, 3. And the math part comes along here. We cross multiply, we get a square equals 87. Again, look at this. We got a square on our a. Since we got a square on the variable we're trying to solve, what we're going to do, you're going to square root both sides here. When you square root something squared, you just get the base value, a. Over here, 87, the only thing that can go to 87 is a 3 and a 29. And neither one's going to help us out as far as reducing. They're not perfect square, and then even then, 3 and 29, they don't have values that have perfect squares. So we'll just leave it as radical 87. Now, if this can reduce, if you do get a number that can reduce, let's say it was 88, and you don't reduce it, there's a problem. Again, you always want to reduce to the simplest form, but this one does not, so we leave it like that. So I'm going to go ahead and erase this information on the triangle, and we're going to try this bottom one out. Oops. So, on here, this time they tell us the value of c is 18. So the whole thing is 18, so that's the hypotenuse. But then they tell us the large leg is 12 radical 2. And they want us to find y. So that means we're going to use the large triangle as the thing we're going to compare to our big triangle. Again, it still goes the same way. Hypotenuse to large leg, so the hypotenuse, 18, is to the large leg, 12 radical 2, as the hypotenuse of the larger triangle, 12 radical 2, is to its large leg, y. So here's a proportion set up. So now we cross multiply. So 18 times y, 18y, equals 12 radical 2 times 12 radical 2. Okay, I'll leave it like this because I want to show you how we're going to do this multiplication. A lot of people ask, how do we multiply things with radicals? Good question. So we multiply big numbers with big numbers, 12 times 12, so 144. And then radicals with radicals. 2 times 2 is 4, but again, they're both under radicals, so you keep the radical. It'll be radical 4. This comes down, so it's 18y equals that. Now you can divide that, and it should divide evenly, but let's go ahead and simplify it first, this whole side. I'm going to write over here. So we got 18y. So when you simplify the radical 4, that becomes a whole number 2. This is still multiplying with the 144. And 144 times 2, this is 288. And then from there, we divide both sides by 18. We get y equals 16. And that should be all, y'all. Let's